All right, we are going to work on the definite integral, and here we are going to find the exact value of the definite integral using limit of the Riemann sum. So here we are working on the definite integral using limit of Riemann sum. Definite integral using limit of Riemann sum. Definite integral using the limit of Riemann sum. So we know that we can find the definite, or we can approximate the definite integral on the interval from a through b using this formula, summation k equal to 1 through n f of x k delta x. We know this. Now, if we increase the interval size, if we increase the interval size and if we maximize the interval size, that is when the size of the interval or the width of the interval is very small and the number of intervals are infinitely many, then if we take the limit in front of this one, that will be the approximate value. I mean, that will be the exact value of the definite integral. You can write it like this: integration from a through b f of x dx equal to limit as x delta x approaches to 0 of the Riemann sum, like this, or this is same as the limit when n approaches to infinity. So meaning of delta x approaches to 0, when we say the width of the interval is very small, that means the number of interval will be infinitely many. So here we can write limit as delta x approaches to 0, or we can write n approaches to infinity. So if we use this formula here, we'll be able to find the exact value of the definite integral. That's how we can evaluate the definite integral using the numerical method or using the limit of the Riemann sum. So make sure you highlight that formula. And in order to evaluate the definite integral using the limit of Riemann sum, you have to use some of these formulas here. Like if you, the first one, the sum of the constant, if you want to add the constant, like 5 plus 5 plus 5 plus 5 plus 5, 7 times, how much it will be? It will be 5 times 7, 35. So sum of constant from 1 up to n will be n times c. That is the formula. Similarly, if you want to add k, when I say k here, k goes from 1 through n, that is like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. That is, you are adding the numbers, the counting numbers from 1 up to n. N can be any. We use this formula, n times n plus 1 over 2. For example, if you want to add 1, 2, 3, there are 3 of them. So if you plug in here, it will be 3 times 3 plus 1, that will be 4 over 2. So 4 divided by 2 is 2. 2 times 3 is 6. So 1 plus 2 plus 3 is 6. So it doesn't look so much interesting here when we are just adding 3 numbers. But if I want you to add 1 plus 2 plus 3 plus 4 plus 5 plus 6 up to 100, then this will be very, very useful. So if you want to add 1 up to 100, then we can easily use the formula and find the value. For example, if you want to go up to 100, this will be 100 divided by 2, which is 50 times 100 plus 1, 101. Now you can see if you multiply that, you'll get the result. What is the result of adding 1 up to 100? It's 50 times 101. So it's quick like that. Similarly, if you want to add the square of the numbers, like 1 is squared, plus 2 is squared, plus 3 is squared, plus 4 is squared, plus 5 is squared, plus 6 is squared, plus 7 is squared, and so on, then we use this formula, n times n plus 1 times 2n plus 1 over 6. Similarly, if you want to add the cube of the numbers, like 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed up to n cubed, the formula is n times n plus 1 divided by 2 whole quantity squared. So these are some of the additional formulas we'll be using while evaluating the definite integral using the limit of Riemann sum. Evaluate the definite integral, that is integration from 1 through 4 of x cubed plus 5x dx using limit of the Riemann sum. So when we say the limit of the Riemann sum, in order to evaluate the definite integral, we use this formula, limit as n approaches to infinity. I'm writing that formula here. Limit as n approaches to infinity of the sum from k equal to 1 through n of f of x k delta x, f of x k delta x. Now here, you can use any Riemann sum. You can use left Riemann sum, you can use right Riemann sum, you can use midpoint Riemann sum. All will work. I'm going to use the right Riemann sum. That means what I'm going to do is, I'm going to use xk as a plus k delta x, because I'm using the right Riemann sum. So I'm going to use this formula and find the exact value of this definite integral. It's going to be the exact value. So let's begin. First, in order to use this formula, you know that we need to find delta x, then f of xk, and we have to plug in there. So let's do that initial business first. Here, delta x is b minus a divided by n, which is equal to b minus a will be 4 minus 1. 4 minus 1 over. So here n goes to infinity. So we don't know the value of n. N is very large. That's what we know. So we just divide that by n. That is equal to 3 divided by n. Remember, n goes to infinity. N is a very big number. So after we have delta x, we try to find xk. Xk is equal to a plus k times delta x, because I'm using the right Riemann sum. That's why in the question they just say the Riemann sum, but here I chose the right Riemann sum. So your a is 1, because we are integrating from 1 up to 4. 1 plus k times delta x is 3 over n. So that is equal to 1 plus 3k divided by n. That is your xk. So f of xk will be, you plug in xk onto this function. So this is my xk. If I plug in there, it will be 1 plus 3k over n cubed, because I'm plugging in here 1 plus 3k cubed, then plus 5 times 1 plus 3k divided by n. We can simplify this one. We can simplify by factoring, multiplying this. So we can multiply and expand this. So in order to expand this 1 plus 3k over n raised to 3, you may want to use this formula. If you remember the formula for the cube, sum of cubes, a plus b cubed will be a cubed plus 3a squared b plus 3ab squared plus b cubed. I'm going to use this algebraic formula in order to expand this. So let me expand that. That will be equal to, okay. So first we have a cubed. This is your a is 1, b is 3k over n. So a cubed is cube of this one. Cube of 1 is 1. 1 plus 3a squared b. 3 times 1 is squared is 1 times 3 is 3. Multiply to 3k over n. That will be 9k over n. 9k over n. That is 3a squared b. Then 3ab squared. 3 times a times b squared. So 3 times 1 times square of this one. So 3 times 1 is 3, square of that. So square of 3 is 9. So 9 times 3, 27k squared over n squared. 27k squared over n squared. Then plus b cubed, cube of this one. 3 cubed is 27. So 27k cubed over n cubed. 27k cubed over n cubed. And then plus, here we distribute this 5. 5, then plus, if I multiply by 5, 5 times 3, 15k over n, 15k over n. Now you can simplify this little bit. You can see here we have a 1 and here we have a 5. So 1 plus 5 is 6. 6. Then plus, here we have 9k over n and here we have 15k over n. And 9 plus 15 is 24. So that is 24k over n. 24k over n. Then plus we have 27k squared over n squared. And then 27k cubed over n cubed. So we got the value of delta xk, and also f of xk. Now we are ready to use the formula to find the exact value of this definite integral. Now, we can use the formula to find the exact value of the integral. Our integral is integration from 1 through 4, integration from 1 through 4, x cubed plus 5x dx is equal to limit as n approaches to infinity, limit as n approaches to infinity, and then summation k equal to 1 through n. That is, first we have to find the sum and then we have to find the limit. Sum k equal to 1 through infinity, 1 through n of f of x delta x. F of x is this one, which we got here. F of xk is that expression, which is 6 plus 24k divided by n plus 27k squared divided by n squared plus 27k cubed over n cubed. That is f of xk. Then we have a delta x. Delta x is 3 over n times 3 divided by n. So we applied the formula and we have written this expression. Now we need to evaluate this expression in order to find the value of the definite integral. Now we are going to evaluate this expression. We are going to find the sum and also the limit to get the exact value of that definite integral. Remember one thing, when you are looking at this summation, when you're working on the summation, k is the variable, k is changing from 1 up to n. N is not changing, n is a fixed, k is changing. And then when we are evaluating the limit, n is changing, n is going to infinity, k is not changing. That is something you need to remember. And first we are evaluating the sum, then only we are evaluating the limit. But before we go that, I think we can distribute the 3 over n into this expression and make it a little more simple. So let's do that. This would be equal to the limit as n approaches to infinity, summation k equal to 1 through n. And I'm going to write it very carefully here because I know that in this case, k is a variable, k is changing and n is not changing. So if I multiply by 3 over n, 3 over n multiplied to 6 is equal to 3 times 6 is 18 divided by n. So that will be 18 divided by n. So nothing is changing there. That's a constant for the sum. Then plus 24k divided by n multiplied to 3 over n. When I'm distributing that, it will be 24 multiplied to 3, and 24 multiplied to 3 is 72. 72, and in the denominator, this n will multiply with n, that will be n squared times k. This k, I'm just writing there, 72 over n squared is a constant for the sum because the only variable is k. So I can write as 72 over n squared times k. Then plus, over here, 3 times 27 is 81, and n times n squared is n cubed. So 81 over n cubed is a constant, then multiply to that k squared there, this k squared. And then plus 3 times 27 is 81, and then n times n cubed is n raised to 4. Multiply 2, there is k cubed. Okay, now we are ready to apply a couple of formulas there. We know that, so this one is a constant. What we know is sum of k equal to 1 through n of constant is n times c. So the first one will be limit as n approaches to infinity. I'm using the sum, so I don't need to write the sum. Sum of the constant is n times the constant. N is n in this case. It is the number on the top. So n times the constant. N times 18 divided by n. Then plus 72 over n squared. That's just the constant. But what I'm doing is I am finding the sum of k. So if you remember that formula, summation k equal to 1 through n of k is n times n plus 1 divided by 2. N times n plus 1 divided by 2. Or if you want to factor this n out, if I want to factor that n out, it will be n squared 1 plus 1 over n divided by 2. If I factor this n out, it will be n squared, 2 in the denominator, and it will be 1 plus 1 over n. So I can write like that. So here the sum of k will be n squared over 2, 1 plus 1 over n. Then plus, if we go to the third term, you have 81 over n cubed, 81 over n cubed. Then we have the sum of k squared, k equal to 1 through n of sum of k squared is n times n plus 1, 2n plus 1 divided by 6. That is the formula. So here what you can do is we can factor n from this one, and also we can factor n from here. So if I factor n from each of these and multiply with that one, it will be n cubed divided by 6. N cubed divided by 6. After I factor n from here, it will be 1 plus 1 over n. And then after factoring n out from here, it will be 2 plus 1 over n. 2 plus 1 over n. So that's what I can write here for that k squared. It will be n cubed over 6, 1 plus 1 over n, 2 plus 1 over n. Okay, we have one more expression there. So let's work on that. It is this one here, which is 81 over n raised to 4 multiplied to k cubed. So now we need to know the sum of k cubed. So if you recall the formula, sum of k equal to 1 through n of k cubed is equal to n times n plus 1 divided by 2 cubed. I mean squared, not cubed, squared. Which is equal to, now here if I factor that n out, it will be n squared, and we are squaring that, so it will be n to the 4. Divided by, I'm squaring this 2, that will be 4. And then after I factor this n out, it will be 1 plus 1 over n, and that is a square there. So that means the last term will be 81 over n to the 4 multiplied to sum of k cubed is this one, n raised to 4 divided by 4, 1 plus 1 over n squared. So that is the result after we evaluate the sum. So in the first expression here, we have n divided by n. So this n will get cancelled. In the second expression, n squared will get cancelled. You can see there. In the third one, here we have n raised to 6. I don't know why I wrote n raised to 6 there. That should be n raised to 3. Maybe you can check it again. That should be n raised to 3 because if you look at the third one, it is the sum of the squares. And sum of squares is k equal to 1 through n. Sum of squared is n times n plus 1, 2n plus 1 divided by 6. So if you factor n from the numerator from here and then multiply here, it will be n cubed over 6. So that is n cubed. So now that n cubed will get cancelled. So let me cancel that. Also in this fourth term, n raised to 4 will get cancelled. So after we cancel all that, let's see what we get. Let's simplify and write the result. That will be equal to the limit as n approaches to infinity. The first one is 18 plus, here we have 72 divided by 2, which is 36. 1 times 1 over n, plus, next one we have 81 divided by 6. 81 divided by 6, you can reduce that fraction and you can write that as 27 over 2. 27 over 2, then you have 1 plus 1 over n and 2 plus 1 over n. Then plus the last one is 81 over 4, and 81 over 4, this one, 81 over 4, it's already a reduced fraction, so you can write as it is. 81 over 4, you have 1 plus 1 over n, quantity squared. Now it is easy for you to evaluate this limit, because when n goes to infinity, when n is very large number, very, very big number, 1 over n is 0. 1 over n is 0, 1 over n is 0, 1 over n is 0. That means what I'm getting is, the first one is 18, plus the second one is, this is 0 plus 1 is 1. 1 times 36 is 36. Plus this one here, 27 over 2 times 1 plus 0, 2 plus 0. 2 times 1, 2. 2 times 27 over 2 is 27. 27. Then plus, now the last one. Last one is 81 divided by 4. 81 divided by 4, because 1 over n is 0, 0 plus 1 is 1, 1 is squared is 1, times 81 over 4 is 81 over 4. So by using calculator, or by simplifying this, even without using calculator, we get 101.25. So that is the exact value of the definite integral. So we can write, let me write that, hence the integration, if you look at that question there, is the integration from 1 through 4 of x cubed plus 5x. Integration from 1 through 4 of x cubed plus 5x with respect to x is equal to 101.25. So this is how we can use the limit of the Riemann sum to get the exact value of the definite integral. This is the exact value of the definite integral. We already know how to evaluate the indefinite integral. It will be an expression, and at the end it will be plus c. But when you're evaluating the definite integral, you will get a number. We use the Riemann sum to approximate the value of the definite integral. But here in this example, we use the limit of the Riemann sum. The limit of the Riemann sum will give you the exact value of the definite integral. So here, integration from 1 through 4, x cubed plus 5x is exactly equal to 101.25. That is the end of this example.